Hello class, welcome to Geometry Lesson 8.1. We're going to talk about right triangles and the Pythagorean Theorem. So our essential question today is, how are similarity and right triangles and the Pythagorean Theorem related? And our learning goal is to be able to prove the Pythagorean Theorem using similarity and establish the relationships in special right triangles. So first thing we're going to talk about is the Pythagorean Theorem. So we actually used this theorem quite a few times throughout the various lessons whenever we dealt with a right triangle. But the theorem states that if a triangle is a right triangle, then the sum of the squares of the legs of the lengths of the legs is equal to the square of the length of the hypotenuse. So if you have a right triangle, then the sum of the squares and for A and B is equal to C squared. Now this also works in reverse, so that means that you can use this to show that a triangle is a right triangle. That is by adding the sum of the squares of the other shorter sides and setting it equal to the square of the longer side. If the statement holds true, then you know that you have a right triangle. So we're going to prove the Pythagorean theorem using similarity. Remember that the previous chapter was all about similarity, similar triangles, and proportions. So given that triangle XYZ is a right triangle, we want to prove that a squared plus b squared equals c squared. So in order to prove this, we're going to break this triangle into a couple of triangles. And so now we have three triangles in total, the original, and then we have the two pieces, that it's the two smaller right triangles. Now, according to the altitude to hypotenuse theorem, which is what we did here by splitting this up by doing a right angle to the hypotenuse, we have three similar triangles according to that theorem. And these are the three right triangles given below. So we got the original and then the two smaller ones on the right. So we know that these have to be similar according to the theorem. So triangle XYZ. So in this case, if you look at the legs, you can kind of see that this one right here, which is looking at this right here, XY, that's the shorter leg. That corresponds to the shorter leg here, which is YW, XY, YW, which corresponds to the shorter leg here, WX. And then similarly, if you look at this longer leg corresponds to this longer leg here, which corresponds to this longer leg here, and then which is given in the statement. So you can use these to help you with the statements. So we know that they're similar, and so we can say that C is to A, and in this case, let's go ahead and use a different color for the hypotenuse here. So this hypotenuse is related to this hypotenuse, which is related to this hypotenuse. So using the proportions and similar triangles, we can see that C is to A, if you're comparing these two triangles, as A, the blue A, is to blue E. And therefore, you can cross multiply. So once you cross multiply, you can solve, you get A squared equals C times E. And then you can take the, you can take the square root and get A, but we're just going to leave it as A squared because we're trying to use A squared plus B squared equals C squared. So we'll tuck that aside for now. Let's look at another proportion. Let's look at the proportion with comparing B, the red B, to F. So B, the red B, is to red F, as green C is to green B. And you can see this in these triangles here. So cross multiplying, we get B squared is equal to CF. And so now we have B squared. And so now we're going to plug these into the Pythagorean theorem. So we know A squared plus B squared. We're going to plug in A squared and replace it with CE, and BF with CF. And then in doing so, we can factor out the C. Since they both have a C in common, we can actually pull it out, and we get C times E plus F. And now E plus F is actually C, which is this green C here. And how do we know that? Well, we know that because if you look at this triangle here, we can see that that's the same thing as this C here, which is combining the E and the F together. And so therefore c times c is c squared, giving us a squared plus b squared equals c squared. And then the theorem is proved. All right, so we used similar triangles to prove the Pythagorean theorem. Now we're going to, given a triangle, we're going to see if it's a right triangle by applying the converse of the Pythagorean theorem. We haven't actually proved the converse of the Pythagorean theorem, and we won't really focus too much on it. I just wanted to focus on the proof of the original Pythagorean theorem, but we're going to apply the converse right now. So if we have a right triangle, or if we have a triangle and want to determine if it's right, then we need to see if a squared plus b squared equals c squared works. So the hypotenuse is always going to be your c, or your quote-unquote hypotenuse. Your longest side is going to be c, and then your shorter sides will be a and b. So applying a squared plus b squared equals c squared. We can say that a is 35, b is 12, but c for sure has to be 37. And then we're going to see if these statements are true. So in order to do so, we'll plug them into the calculator. So it turns out 35 squared is 1225. 12 squared is 144. And 37 squared is 1369. So then if we add these together, you have 1225 plus 144. You actually get the same thing on both sides. So this is true, that you get 1369, and therefore we can say that this is indeed a right triangle. And in fact, the angle for the right triangle is right here. All right, so we talked about how to use the converse of the Pythagorean theorem to identify a right triangle. Now we're going to talk about simplify square roots. The reason why we want to talk about simplifying square roots is because since we're dealing with the Pythagorean theorem and we're going to have square roots involved and squares, we need to know how to simplify the square roots in case we have something that that's not a perfect square. So what we want to do here is, in order to simplify 360, the square root of 360, we need to break this down into its perfect squares, into its factors, such that one of them is a perfect square. So in this case, remember that a perfect square is, for example, 1 because 1 squared is 1, 4 because 2 squared is 4, 9, 16, 25. Those are perfect squares because you can take the square root of them and get nice whole numbers. Okay, and that's what we want to look at, those nice whole numbers. And so if you were to use the perfect square of 36, then 36 goes into 360. So we're going to use that here. All right, since we know that 360 is 36 times 10, we can split it up like that, and we can split it up into two square roots, square root of 36 and square root of 10. And the square root of 36 is 6, because 6 times 6 is 36. So we got 6 times square root of 10. And that's how you simplify the square root. Now 10 can't be broken down any further because you have 5 times 2. However, so you can break it down into 5 times 2. However, 5 and 2 are not perfect squares. So you want at least one of them to be a perfect square. Now for the second one, we have a 5 on the outside, but we want to focus on the 80. So 80, in this case, if you look at the perfect squares, so we know that for sure 8 goes into 80, but we also know that 16 goes into 80. So we're going to do 16. We want to choose the perfect square, the biggest perfect square for this, so that we save ourselves some work. So we know that this is 16 times 5. So the square root of 16 times square root of 5. And then we're going to bring down this 5 off beside it. Now the square root of 16 is 4. So we got 5 times 4, and then we got square root of 5. And then 5 times 4 is 20. So we got 20 square root of 5. Now if you were to break up the square root of 80 into, for instance, 4 and 20, that's perfectly fine. But you would have to split up the 20 into another 4 and 5. And so you'll end up having to have just a little bit more, an extra step here. You'll have 2 square roots of 4, and then square root of 4 is 2, and then you have 2 times 2, which is 4. And then, of course, you would have to bring down this 5 to multiply it to make 20. So there are multiple ways of solving these, but ideally you want to minimize the number of steps. All right, so for example 4, we want to simplify the square roots for, this is a specific type of simplification known as rationalizing the denominator. So rationalizing the denominator means you're going to get rid of the denominator in, or you're going to get rid of the radical in the denominator, okay? So in order to do this, we need to multiply by the same radical on both sides. Now the radical, remember, is just this radical, this square root symbol. That's what I mean by the radical. But to get rid of this radical, or the square root, you have to multiply by the same square root on both sides. So you're gonna, whatever you do on the bottom, you have to do on top. So square root of 5 times square root of 5 is square root of 25. And then 10 times square root of 5 is just that, 10 times square root of 5. And then we know that square root of 25 is 5, and therefore we get rid of the radical. So we got 10 square root of 5. So no more radicals in the denominator. 10 divided by 5 is 2, so we're left with 2 square root of 5. Okay, so it's just a form of simplifying so that we can eliminate that radical in the denominator. So now let's do the second one. We want to get rid of the square root of 6, the square root there. So we're going to multiply by the same radical, do the same thing on top, get 4 times square root of 6 over, then you got square root of 6 times 6 is 36, and then square root of 36 is 6. Now 4 over 6 can be reduced. You can reduce that. So let's go ahead and divide the top and bottom by 2. And in doing so, you get 2 square root of 6 over 3. All right, so we talked about how to simplify radicals, rationalize the denominator. This time we're going to switch back to the Pythagorean theorem and find the missing side. Now when we do this, we're not going to have a perfect square root, and so we're going to have to simplify using what we used in the previous 2 examples. So we have a right triangle, we have 2 legs, 9 and 9. We want to figure out the hypotenuse C. So we have here 9 squared plus 9 squared equals C squared. And we got 9 times 9 is 81. Then we got another 81 here equals C squared. And then 81 plus 81 is 162, which is equal to C squared. And so we're going to have to take the square root on both sides here. And so C is equal to the square root of 162. So now we got to break that down, break down the square root of 162. So we know that, let's see here, we know that 62 is divisible by 2, but we want it to be a perfect square. So if you did 162 divided by 2, you're going to get 2 and 81. Now 81 is a perfect square, so that works. So we're going to split this up into the square root of 81 and the square root of 2. And then square root of 81 is 9. So we get 9 times square root of 2. All right, so for part B, we have here a 30, 60, 90 triangle. We have another right triangle. And we want to figure out this side. We'll call this side A. So we got A squared plus 6 squared equals 12 squared. We have A squared plus 36 equals 144. Then we'll go ahead and subtract 36 on both sides. So we got A squared equals 144 minus 36, which is 108. And then we'll take the square root of both sides. We'll split up the square root of 108. So 108 is divisible by 36. So we can split out 108 into 36 and 3. And I use 36 because that's a perfect square. Square root of 36 is 6. So we got a is 6 times the square root of 3. So it turns out that these two triangles are special right triangles. We have the one on the left, which is a 45, 45, 90. And the legs are the same. And the hypotenuse is the leg times this square root of 2 factor. Now the one on the right is a 30, 60, 90 triangle. And the shortest leg is a number. And if I double that number, I get the hypotenuse. And the second longest leg is that the number for the shortest side times this square root of 3 factor. And this is always the case for these two special right triangles. So for the first one, the one that we discussed was 45, 45, 90. And in this type of triangle, you have the two sides are the same, the two legs. And then the hypotenuse is given by the leg times square root of 2. So recognize this pattern so that you can use this every time you encounter a 45, 45, 90 triangle. Now for the next one, the 30, 60, 90, we have the shortest side, we'll call that S. Then in order to calculate the second longest side, I multiply S by the square root of 3. And then to get the longest side, I multiply by the S by 2, I double it. All right, so example 6, find the missing sides using special right triangles. Now we know this is a 45, 45, 90 triangle. It's listed here. Now this is the hypotenuse. Remember that the 45, 45, 90 theorem stated that these are like S or X, whatever you want to call it. And then the hypotenuse is that times the square root of 2. Hold on, let me draw it again here. And so we know that 12 is equal to S square root of 2. So we're going to set those equal to each other. So we get 12 is equal to S times square root of 2. The hypotenuse is equal to that. And then we can solve for S or X, whatever you want to call it, and then by dividing by square root of 2. And so that gives us the missing side. We know that each of the sides is 12 over square root of 2. So these are the sides. So going to erase this and just write these down as this side. So that's the same on both sides because it's a 45, 45. However, we want to simplify this leg. We don't just want to write it as 12 over square root of 2. And we're going to use the technique that, remember, that I showed you, that we showed in the previous slide, where you have to get rid of the radical. So in order to do that here, we're going to multiply the denominator by the same radical, top and bottom. So we have 12 times the square root of 2 over, and then we have the square root of 2 times 2 is 4. The square root of 4 is 2. And then we got 12 divided by 2 is 6. So we got 6 times square root of 2. And that will take care of the missing sides. All right, so the one on the triangle on the right, we know that this is 20, so this has to be 20. And because the two legs are the same, that means we have a 45, 45, 90 triangle. And so to find the hypotenuse, you simply take the side and multiply by square root of 2, and you're done. All right, so looking at the next example, we have 30, 60, 90 triangle. Remember that for the 30, 60, 90 triangle, you have the shortest side is the side next to the 60. So this is the shortest side, we call that S. And the hypotenuse is always double S or double X, whatever that variable, whatever you want to call that variable. And then the second longest side, this 30-degree side, is the shortest side times square root of 3. So since we know the hypotenuse is 12, that means the shortest side has to be 6, because 12 divided by 2 is 6. And then take that 6 and you multiply by square root of 3, and that gives you the second longest leg. And you're done there. Using the same model, we have here, we don't have the shortest side, we have the second longest side, the one beside the 3 here. So we know that 5 is equal to s square root of 3. So I'm just going to set those equal to each other. And I want to solve for the shortest side. So I'm going to divide by square root of 3. And that gives me s is 5 over square root of 3. So I now have this side here. However, I want to simplify this. So I'm going to multiply the top and the bottom by the same radical to get rid of that one on the denominator. And I'll get 5 square root of 3 over square root of 3 times 3 is 9. So square root of 9 is 3. And so that's my side here. All right, next we'll get the hypotenuse, which is pretty simple. All you got to do is double the shortest side. So it's going to be 2 times 5 or 10. All right, that's going to do it for the video, guys. So I hope you found this useful. I hope you took a few things. And as usual, I'll see you in the next one.